Hello everyone. Let's continue solving question based on numericals based on equilibrium of beams. Let's read the question. Determine support reactions for the beam loaded and supported as shown in the figure. Diagram is given with the question itself. We can see the beam AB which has one uniformly distributed load UDL or a rectangular load having intensity 20 kilonewton per meter spread over 4 meter length. At point D we have a moment 60 kilonewton meter. Our aim is to find out reactions at A and at B. Now here the symbols of the supports are not given. We have just shown the arrows for the reactions. So let's assume that these are going to be simple reactions. Assuming that these are simple reactions, let's solve how much is the reaction at point A and how much is the reaction at point B. Let's begin with this. We know the beam has to be in equilibrium. So first we should mention it. For equilibrium of beam, we are going to solve further. Let's draw FBD of the beam. Now even though we don't have any supports provided here as a hinge or roller or fixed support, still we have to convert this UDL into its equivalent point load. Even though the support reactions are already given to us in form of arrows, still we have a UDL which has to be converted into its equivalent point load. So let's see how we can do that in the FBD. Let's draw the length AB first. At end A we have, let's call that reaction RA. Then further, over the 4 meter length of the beam, over the 4 meter span, we have this uniformly distributed load having intensity 20 kilonewton per meter. We know that if we have a UDL or we have a rectangular load, it should be converted into its equivalent point load by finding out area of this rectangle. Now area of the rectangle is nothing but intensity into the length or the span over which the load is distributed. So 20 into 4, that will be 80 kilonewton, and this 80 kilonewton single point load we will have to locate exactly on the midpoint of the length AC. So if I locate midpoint of the length AC, here I have to locate the equivalent point load, which is nothing but 20 into 4, 80 kilonewton, and this is the point C, which was A to C distance was 4 meters. So we have got split it into exact two half parts, 2 meter and 2 meter each. After point C at D, which is 2 meters away from point C, we have got a moment which is shown in the anti-clockwise sense. The arrow is already given, kilonewton meter. The unit is given kilonewton meter, so we know it is a moment 60 kilonewton meter. At point D it is given, and further at point B we have a support reaction, let's call that RB. We have to find out these two unknowns, RA and RB. Let me write these dimensions. Okay, so we have to solve this for RA and RB. We know the system is in equilibrium. It is a non-concurrent force system, so we have to use conditions of equilibrium for solving this. Even though we don't have a hinge here, we have two unknowns RA and RB. About any one point, either at point A or at point B, I can apply the condition of moment to find out the other remaining unknown. Let's apply condition of moment at point A. Let's say summation MA equals to 0 using anti-clockwise positive and clockwise negative. Let's apply 80 into 2. Clockwise rotation of 80 kilonewton about point A will give you minus sign, force multiplied by the distance. Here we have already a moment which is rotating in anti-clockwise sense, so that should be taken as plus 60. We are not going to multiply the moment by any distance, that we have already discussed. RB should be multiplied by distance measured from point A, which is 8. RB is going to have anti-clockwise rotation about the fixed end A. If you are considering A as the fixed point of the rod or the beam, and the action of RB, if you see, it's going to rotate the rod or the beam AB about point A in anti-clockwise sense. So that is positive, and that total is equals to 0. So we are going to have RB equals to, bringing the terms on the other side, 160, this will be plus, and this minus 60, 60 will bring on the other side, it will become minus 60 upon 8. So 100 upon 8, the answer is 12.5 kilonewton. RB we have assumed upward, for which we have got positive answer, so this is the correct direction, and this is reaction at the end B. Let's find out reaction RA. There are no horizontal forces existing in the system, only vertical forces. So RA should be calculated by using summation Fy equals to 0, upward positive, downward negative, using this condition. So now using this, we have unknown RA taken in the upward direction, so positive, minus 80. We don't have to add or subtract this moment now. We have to just use the vertical components existing in the system, and that is now remaining is RB, which we have calculated as 12.5. It is upward, so taken positive, equals to 0. So RA is going to be simply equals to 80 minus 12.5, so that will be 67.5 kilonewton. RA positive, we have taken RA in the upward direction, so that assumed direction is correct. So these are our answers. Right. So let's move to the next numerical. The third one, a simply supported beam AB of span is nothing but length, the total length of the beam AB is given 6 meter, is loaded and supported as shown in the figure. Find reaction supports at A and B. Again, in this diagram you can see that specifically we here it is not mentioned whether at point A what kind of support is present. Directly the reactions are given as arrows, and there are only two vertical arrows given respectively at point A and B, one each at point A and at B. So let's assume that this is a simply supported beam, and our aim is to find out these two unknown reactions at A and at B. Again, here we'll have to draw the FBD for converting this uniformly varying load UVL, or the triangular load, into its equivalent point load. So let's draw the FBD first. In the FBD, at point A, the unknown reaction RA, then we have at 1 meter distance the applied point load 10 kilonewton, and then after this point load, after sparing 1 meter distance, the triangular load starts, and it is spread over 2 meter length. So span of the triangular load is 2 meter. So let's mark this 2 meter distance. After that, at 1 meter distance you have got the 10 kilonewton load, and further after 1 meter distance again you have got the unknown RB reaction at point B. So now whatever 2 meter distance we have left in between where triangular load was present, we have to represent the equivalent point load. We know for a triangular or uniformly varying load, the equivalent point load, the magnitude of the equivalent point load is calculated as area of the triangle. So half into base into height, that is going to be the area of the triangle. So it will be half into 2 into 15. So the total magnitude is going to be 15 only. But where exactly that point load we have to locate? Always from the maximum intensity point at distance L by 3, where L is the span over which the load is distributed. So now the span is 2, and from the maximum intensity point at distance L by 3. So from this point where the load was from here to here. This is the span over which the load was distributed, and this is the point where the maximum intensity was present. So from here, at distance L by 3, that is 2 by 3, this is the distance 2 by 3 meters over which the load has to be shown. At this point the load has to be shown, and the remaining distance is going to be 2b by 3, or let's say 2l by 3. The L length of the span is 2, so 2 into 2 upon 3, so that will be 4 upon 3. Okay, so this much is the remaining distance. And as we said, the magnitude of the point load is going to be equals to area of the triangle, so half into the base into the height, so that becomes simply 15 kilonewton itself. Okay, so let's mark rest of the distances. 1 meter, 1 meter, and here this one was also 1 meter, and the remaining one is also here 1 meter. Okay, we know that 4 by 3, this distance is approximate 1.33. So according to that, whatever is the remaining distance out of 2 meter, if you are subtracting 1.33, the rest of the distance is 0.67. I'm not writing here this distance as 0.666. Instead of that, I'm just rounding it, rounding off the last digit, that is 6 to 7, so that the total distance addition of these two numbers is going to be equals to 2 exactly. That way we will increase the accuracy of our answers of RA and RB. Let's use the conditions of equilibrium. For equilibrium of beam, let's say summation MA is equals to 0, taking anti-clockwise positive and clockwise negative. Let's minus 10 into 1 minus 15 into, from point A up to this 15 kilonewton load, the distance is 1 plus 1 plus 1, that is 3.33. Rotation is clockwise. Further, this vertical 10 kilonewton load. So this vertical 10 kilonewton load should be multiplied by this much. We have it is already 3 plus 2, that is 5, and the rotation, as we said, is anti-clockwise, so it should be taken positive. RB is also going to generate anti-clockwise rotation, so that should be also positive, and it should be multiplied by the total length, because we are calculating moment about point A from A to B. This total distance is 6, and that is going to be equals to 0. The total sum of all the moments about point A is 0. Let's calculate RB. RB comes out 1.658. It should be in kilonewton, and we have assumed RB moving vertically upwards, so the assumption is correct because our answer has become, we have got the answer positive. So whatever assumed direction of RB is there, it is correct. Let's use summation Fy equals to 0 to find out the other remaining vertical unknown component, taking upward positive and downward negative. So we have RA minus 10 minus 15 plus 10 plus RB, which is 1.658, that equals to 0. Let's calculate RA now. So 10 plus 15, that should be 25, minus 11.658. RA is 13.342 in kilonewton, which will be in the upward direction. That is our answer for the other unknown. Let me just verify this. Yep, fine. Let's go for the next sum. Let's solve the next sum. Here we have to determine reactions at point A and B for the beam loaded and supported as shown in the figure. So in this figure we can see that at A we have a hinge support and at B we have a roller support. So let's draw the FBD and remove the supports, and instead of these supports show the reactions. For hinge we have always two reactions, one horizontal and vertical. It is at point A. Let's call it AX AY. Now we have got two moments. The curved arrow always represent moment. The unit is kilonewton meter. So let's represent these two moments. One is anti-clockwise, the other is clockwise. And at point B, the roller is kept on the horizontal surface, so reaction exerted by the roller has to be vertical, that is perpendicular to surface. Let's call that RB. This is at point B. The distances are given. Let's solve this as usual. Now we have a hinge point, so without any doubt, for equilibrium we will apply the condition summation M A equals to 0 about the hinge point, taking anti-clockwise positive. So moment of AX and AY about point A is going to be 0. Here we have got a clockwise rotation 50 kilonewton meter, which should be taken negative. Anti-clockwise rotation 20 kilonewton meter should be taken positive, and the moment given by RB will be again anti-clockwise. The load should be multiplied by the distance. We have not multiplied these moments by any distance because those are already moments, remember. RB should be multiplied by 6 and should be equated to 0. So now we have got RB 50 minus 20, that is 30 divided by 6. So that will be 5 kilonewton. RB is vertically upward. Assumed direction of RB was upward, so same is the direction. We have got positive answer for RB. Let's find out AX and AY. As we previously also mentioned, if AX is the only horizontal component present in the entire system, AX has to be 0. So even if you say summation Fx equals to 0 and then you call that AX has to be equals to 0, that is fine. Or otherwise directly you can mention AX is 0, and because of that whatever AY is there, same has to be the resultant of AX and AY, RA. Let's find it out by using condition summation Fy equals to 0, taking upward positive and downward negative. So we have RA, which is nothing but our AY itself. Now we are not going to consider these moments at all because these are not the loads, these are moments. For loads already multiplied by distance, so we don't have to convert these also into any loads. These are moments, keep those as moments itself. Don't take those in the conditions of summation Fx and summation Fy. The only other remaining load, the vertical load, is RB, which we have calculated, plus 5, and that is going to be total equals to 0. So here we are getting RA is equals to minus 5. Now if for the solved question we are going to have negative answer, what does that represent? We know that if for the calculated answer we get positive sign, that represents our assumed direction is correct, but if we get negative sign, that means our assumption has gone wrong. RA, rather the AY component, which is nothing but RA itself, this vertical component is not actually going upward, but it has to be in the downward direction. So that is the correct correction in the direction of ay component, which is, we said, is equals to the resultant itself. So this is how the question has to be analyzed for the support reactions of the hinge and the roller at A and B. Let's go for the next one. Question says determine reactions for the beam loaded and supported as shown. Again, here you can see the beam AB, which is 4 meter long and supported by hinge at A, supported by roller at B, and there is one vertical arm to the given beam, at the end of which we have got 100 Newton loads applied horizontally in opposite directions. The vertical arm is 1 meter long on the upper side and 1 meter long on the lower side of the horizontal beam AB. Let's see how we can solve this. First of all, as usual, let's draw the FBD. Now here, let's show the horizontal and vertical components of the hinge AX, AY, and we have got this 1 meter horizontal arm extended vertically on either sides, on the upper side as well as on the lower side, and at the end of those that vertical arm, we have two horizontal forces, 100 Newton each, applied in the opposite directions, and reaction of the roller RB. Roller is placed on the horizontal surface, so reaction of the roller has to be vertical, always perpendicular to the surface. We will have a single reaction for the roller, that is well known, and the distance is 2 meter each, and the vertical distance for the arm is 1 meter each on the upper side as well as on the lower side. Let's solve this for RB first. As usual, let's apply condition of movement about point A, summation MA equals to 0. So that will have, now while calculating movement of this 100 Newton force, which is a horizontal force, I must look for to multiply horizontal force vertical distance. We know that force is multiplied by perpendicular distance from the fixed point for calculation of the moment. If 100 Newton is the horizontal force, I need vertical distance from point A up to the 100 Newton force, which is nothing but the 1 meter vertical distance here. So 100 into 1, the rotation of this force about point A is going to be clockwise, so let's take it minus, and further the other 100 Newton force, which is below the beam AB, again horizontal force multiplied by the vertical distance. The rotational sense we can see is clockwise only, so minus 100 into 1, and then the remaining component, remaining reaction RB for the roller, it has to be multiplied by the distance from point A. 4 rotation will be anti-clockwise positive, and that is total equals to 0. So we have got 200 is equals to RB into 4. So RB will be simply equals to 200 upon 4. So that should be equals to 50. 50, oh, it's Newton only, not kilonewton. 50 Newton. We have found RB. It is positive, so upward is the correct direction for RB. We have assumed the same one. Now let's find out AX and AY. Here, let's apply summation fx is equals to 0 for finding out AX, as usual, taking right positive and left negative. So AX, our assumption for AX is right, so taking it positive. This 100 Newton force going right, so that is also positive. This 100 Newton left, so minus 100. That's it. These are the only three horizontal components existing in the system, and that is equals to 0. Now we can see that plus 100 minus 100 is going to be equals to 0. So at the end, AX itself is going to be equals to 0. Fine. No issue at all. Summation Fy equals to 0. Let's use the third remaining condition, upward positive and downward negative. Now because AX has become 0, we can say that AY is going to be the vertical component of the hinge itself is going to be equals to the resultant of the hinge. So I can say that AY itself is going to be equals to RA, and then we can say RA plus RB. RB we have calculated 50. For RB we have found that upward is the correct direction, so we have taken it plus 50 and that is equals to 0. But after solving this we can see that RA comes out minus 50 Newton. So what do we mean by this minus sign? Whatever assumption of AY in our diagram is, that is vertically upward, but for this assumption if we have got negative answer, our assumption has gone wrong, we should correct it. So 50 Newton RA is not moving upward, but it has to be in the downward direction. So these are the correct directions and the magnitudes of RB and RA, the hinge and the roller reactions, that those we have given in the diagram. Let's try to solve one more question and then we can wind up. So let's see. In this question now, determine support reactions for the beam loaded and supported as shown in the figure. The 50 kilonewton force is inclined at 30 degree to horizontal. You can see in the diagram the the load 50 kilonewton is inclined and angle is not mentioned over here, but it is mentioned in the statement given in the question. So keeping in the mind, most of the time we just tend to look at the diagram and we start solving the question, but some very crucial information given in the statement we miss out, and then we stuck up somewhere in between the calculation. So don't do that. Always make a habit of reading the given questions thoroughly, then see the diagram, look for all the information given in the diagram, draw the FBD, and then you can start solving it. Let's draw the FBD. We have to find out the support reactions at A and at point B now. Left AY component, whether it is upward or downward, we have just assumed certain directions here. We have got this inclined 50 kilonewton load as mentioned in the question. It makes 30 degree angle with horizontal. So let's show that. So this from point A up to the point of application of 50 kilonewton, this distance is given 2 meters. Further, at 1 meter distance from here, one rectangular load has started. We know that for a rectangular load, if we want to find out the equivalent point load of this, we'll have to calculate area of the rectangle. The intensity itself represents the breadth and the span, the 2 meter span on which the UDL is distributed, uniformly distributed load is present, that is 2 meter. So length into breadth, that is the area of the triangle, area of the rectangle, and that will be the magnitude of the point load. So 15 into 2, 30 will be the magnitude of the point load, and it should be located exactly on the midpoint of this span 2 meter. So I'll locate the midpoint of the span 2 meter, and 15 into 2, that will be 30 kilonewton. So let me show these dimensions appropriately. It is getting split into 1 meter distance each because it is located exactly on the midpoint of the 2 meter distance. This is somewhere, this is the position of the point B at which we have got a roller support. So let's show single reaction RB, and at the end of the beam 30 kilonewton load, which is over at the distance 1 meter again from the end B. So here now we have to find out these unknown components AX, AY and the reaction RB. Here also we have to use the same procedure it is a non-concurrent force system under equilibrium. We have to use conditions of equilibrium and find out the unknowns. As usual, if at all you have a hinge point, always prefer the condition of moment about hinge point and solve the remaining unknown, which is nothing but RB in our case. Here one very specific point we have to note down. 50 kilonewton is one inclined force, so we must resolve it, and the resolution has to be done at the point of application. If I resolve this 50 kilonewton force, the horizontal component is going to go left and the vertical component is going to go down. So we will have 50 cos 30 and 50 sine 30, these two components for the given inclined force 50 kilonewton. Let's consider equilibrium of the beam and apply the conditions, starting with moment, condition of moment about point A. As usual, anticlockwise is positive. Of course, moment of AX and AY components about point A is going to be 0. So we don't have to bother about these two. Further, for this 50 kilonewton now, instead of the force, inclined force 50 kilonewton, let's consider these two components and calculate moments of these two. 50 cos 30, horizontal component is going to pass through point A, its moment is going to be 0. This 50 sine 30 vertical force should be multiplied by the horizontal distance, which is 2. So 50 sine 30 into 2, the rotation is going to be clockwise, so should be taken negative. This 30 kilonewton load also is going to generate clockwise rotation. It should be multiplied by perpendicular distance from point A, which comes out 4. RB is going to have anti-clockwise rotation about point A. So RB multiplied by the perpendicular distance, this is 4 plus 1, 5. And the remaining 30 kilonewton, which is having clockwise rotational sense about point A, so minus 30 into 6, and that total sum is going to be equal to 0. Let's find out RB. RB comes out to be 22 kilonewton with positive sign, and that represents our assumption for direction of RB is correct. It is moving vertically upward only. Now here I cannot say that AX is going to be 0. Why? Because in this FBD, AX is not the only horizontal component present, but there is another horizontal component also, 50 cos 30. So we'll have to appropriately apply the condition summation fx equals to 0. We have to take right positive, left negative, and find out the unknown AX component. So our assumption is AX going right, so for that we'll take positive AX. This horizontal component is going left, so that will be minus 50 cos 30, which going to be equals to 0, and we are having magnitude of AX as 43.30 kilonewton. So that's our answer for AX component. Now we have got positive answer for AX, so our assumption of direction for AX component is correct. It has to be in the direction towards left only. Further, we can't stop here. Further, we'll have to find out the AY component as well. So for that, as we know, we have to apply the condition summation Fy equals to 0, where upward should be taken positive and downward should be taken negative. Let's see what are the vertical components existing in the system. AY upwards minus 50 sine 30 minus 30 for this 30 kilonewton load RB, which we have just now calculated, which is upward, and 22 kilonewton and minus 30. That total is going to be equals to 0. Let's find out AY. 83 kilonewton with positive sign. So our assumption of AY is correct. It is vertically upward only. Now once you have calculated AX and AY, knowing that your AX component is going somewhere in the right direction, AY component is going in the upward direction, the resultant of these two is going to be somewhere in the first quadrant. Let's call that RA, applied at point A, and then you can find out magnitude and direction of the resultant reaction RA as RA and the angle alpha. And you know that this RA is going to be equals to square root of AX square plus AY square. Let me calculate this. It comes out 93.615 kilonewton, and the angle alpha, the direction can be calculated as tan inverse of AY upon AX, where you have to neglect the signs of AY and AX components. Here both AY and AX are positive, so let's substitute these values. Substitute the values. 83 divided by, that is AY divided by AX, 43.3, and the answer comes out, I have taken the tan inverse of that also, so answer is 62.449. let's round it off and make it 62.45 degree. So this is nothing but the angle made by the resultant reaction with horizontal. So here it's necessary, whenever you have a hinge support and you have got horizontal and vertical components, both AX or AY, out of these two, none is the zero component. In that case, you will have to find out the resultant reaction of the hinge in its magnitude as well as in its direction. So these are some representative kind of questions which are asked in the university exam. Do follow similar numericals given in the textbook and try to solve those. Few more variety questions we will solve in the next lecture of equilibrium of beams. Thank you.